staff of the institute, they insist that as many people as possible fill in the questionnaire that you have on the table in front of you. So those who have not yet done so, please do it before you leave, if you leave. And I said something about the website. Those who still don't know that, you see, this announcement there says that seminars will be available on the web app. That means that all the lectures actually are recorded and you can listen to them again. So, and again, sometimes 3 times again doesn't. Anyway. Okay. Yeah. So you have switched on your microphone, right?
Yeah, I think so. Yeah.
You did. Okay. So we have the next talk by Garcia-Garcia from Princeton. It's nice that he somehow stepped in at some stage. Understand localization from theoretical aspects to applications.
Well, first I want to thank the organizer for inviting me to this conference. So since I have 45 minutes, I decided to talk about 3 different projects. So in that way, if you fall asleep after 10 minutes, then you can recover. Because the projects, they are, the subjects, they are, all of them are about understood localization, but they are different. So the first thing that I want to talk is about our recent work about analytical approach to a D-dimensional Anderson transition with D bigger than 3. So essentially what I want to do, the problem is just to compute critical exponent, for instance mu, which control the divergence of the localization length, level statistics using some analytical approach. So first I'm going to discuss other approaches in the literature. So it's like locator expansion, the one parameter scaling theory that for physicists maybe all of you of course know, but maybe mathematicians they are not that aware of some of them. Also self-consistent condition to deal the metal insulator transition. And then I'm going to propose something which is essentially a combination of these 2. So let's start with the paper by Anderson, which you know got many citations. What he wanted to know, it was simple. It's just you take a particle, what happened? If a particle has random potential and you wait, and so what happened? So so he got all the answers right. So for instance, predict a metal insulator in 3 dimensions, localization in 1D. But the problem is that the method that he used, it was perturbation theory. It's not the problem that what people say is difficult to follow. It's that it's impossible to follow because the method itself has the problem of small denominators. So if you do perturbation theory and you have small denominators, then he was so clever just to know exactly what was right, what was wrong, to choose what was right. But this was a fundamental problem. The problem of small denominators. That actually this was after many years tackled in the mathematical literature by Spencer and Froley, using a kind of CAM approach. Then,
Does
yeah.
the method also predict a transition in 1 dimension?
No, transition in 1 dimension, no.
So if you were following Anderson's original paper, would you see the difference between 3 and 2 and 1 dimension?
Between 3 and 1, yeah, sure. So he predicted in 3 dimensions you have a metal insulator transition, and 1D you should.
Not in 2.
No.
It seems that 1 dimension it is more diffuse.
Yeah, I mean this was after that, but implicit in the Anderson paper is also that in 1 dimension. He was interested also in 3 dimensions in the paper. Okay. Then the question is that for many years, interactions. Even Anderson himself, he was worried about interaction, even general disbelief. Okay, this is what he said. But my recollection was, on the whole, the attitude was one of humor on me, because they could not understand the calculation. It was something counterintuitive because it was again the spirit of band theory. Then the next development, it took place, at least from my point of view, like in '73. Also was Buchakra, Anderson, Tholes. It was a self-consistent condition. So what they start with a one-dimensional. With a tight binding model, and they want to compute how behave the self energy. And what they do just a perturbative calculation. So this is one loop calculation. But then they compute this guy, the self energy, self-consistently. So here, if this is one order perturbation theory, he should be here. You should see the free one. But what they do is they do this self-consistent condition. This was a big improvement because now, still in this approach, you don't have control on the approximation, but you know that is valid for a Kelly tree. And this Kelly tree means this is the limit when d goes to infinity. So this should be correct for d going to infinity. The problem is that you don't know what are the finite dimensional correction. So you know that, but you don't know if the correction to this result will go like 1 over d squared. You don't know, and you cannot get that from this. Essentially, the technicalities is that you just add a little bit imaginary part to the energy, and then you solve this stochastic equation, and then the probability distribution of the imaginary part of this guy is sensitive whether you have a metal or insulator, so you can distinguish that. So you expect that for a metal, something which doesn't go to 0. For an insulator, it should go to 0 when the imaginary part goes to 0. Also, with this method, you can compute things like the critical disorder. So the critical disorder at which the metal-insulator transition occurs. And then you get results that are reasonable in the sense that is up to factor, let's say, 2 or 50% okay. But also they are not precise. But this was a big development. From my point of view, in the way that we understand the metal-insulator transition. Then the next thing was the scaling ideas, that they was based on ideas of Thouless, Wegener, and then the famous paper of the Ganov 4 in 79. The idea of scaling is simple. So you define, well, there are two different ways to introduce the dimensional Thouless conductance. One is to define the ratio between two energies. So one is the Thouless energy, which is related to the travel time to cross a box of size L, and then a quantum scale, which is the mid-level spacing. So then obviously, if G is much larger than 1, this is like the behavior of a metal in the sense that the system doesn't feel that the spectrum is discrete. And the opposite applies. If this is smaller than 1, that means that the system must be an insulator because this guy is much bigger than this guy, so it's difficult to move. So if you assume that you have diffusion motion, then you get that the dimensional conductance should go like the size of the system to d minus 2. But now, very simple thing, you just get what is called the scaling theory of localization. So you just assume that the changing conductance with the system size only depends on the conductance itself. And then assuming that the beta function which controls the running of the dimensional conductance is you assume that it's a monotonous function, then you can prove that in 1 dimension you have localization, and in 3 dimensions you have metal-insulator transition. In the case of 2 dimension, as you see, the conductance goes like it's a constant. So the beta function in this limit, in the metallic limit, is equal to 0. So then you need to compute the leading quantum correction. So this was done in the 80s, and what people found is that the leading correction is negative. So that means that in 2 dimensions, always the system is in the insulator side. Of course, this is for mathematicians. They don't believe this calculation too much. But for a physics level of, say, certainty, is fine. So we believe that this is in 2 dimensions we don't have a metal insulator transition. So what are the predictions of the scaling theory for the transition? So one important prediction, which maybe is the most important prediction, for at least for what I'm going to say, is that if we are close to the metal insulator transition, we have anomalous diffusion. So it's not the system is not like a diffusive conductor, but the diffusion is anomalous. And depending on the dimensionality of the space, is more or less anomalous. But it is anomalous. As a consequence of that, we can think of this like the diffusion coefficient become or momentum dependent or space dependent, independent on what you want to compute. This was first. There are numerical simulations by Chalker in the early 90s about these issues. Then another, it's evident that if you are at the critical point, precisely at the critical point, the dimensional conductance is a scaling variant. So this is important if you compute things like level statistics. So you know that everything that you compute, if you are right at the critical point, should not depend on the size of the system. Now you will see why this is relevant. Then the next development, which came a few years later, was also a self-consistent condition, but instead of Thouless, Abu Chakra, Anderson, it was starting from, not starting from a tight banding model, but starting from the metallic side. So you do exactly the same, but starting from the metallic side. And essentially what they did was a quite technical calculation. They relate the leading ladder diagrams to the leading weak localization correction, which are given by this kind of diagrams, which are Couperons. So you just loop in the opposite direction. Okay, and then so you get this self-consistent condition, which is similar to the self-consistent condition of Thouless Abu Chakra.
No, it is not. Because for the unitary ensemble, this doesn't give anything.
No, for the unitary, you cannot, if you use exactly Wolfe-Bolhar, you cannot. I mean, but this is also because the way that it's doing the calculation. Think that if you are in the insulator regime, it doesn't really matter if it's unitary, if it's orthogonal, but here it will be very important. We expect different.
It is that this approximation, not approximation, this self-consistency equation is not equivalent to that.
No, I'm not saying that it's equivalent because they are for completely different situation. Actually, this is supposed to be valid only close to 2 dimensions, and the other is supposed to be valid when d is much larger than 1. What I want to say is that they are the similar ideas, but it's not equivalent, that you can pass, of course. Actually, they are in some sense opposite, because they want to describe different regions or different dimensionalities. Okay, so what are the predictions of this self-consistent condition? So you can also, they predict a transition for d bigger than 2. It's supposed to be correct for d close to 2. And the problem is that also you can compute critical exponent. Okay? Then if you compute critical exponent, what you get is this simple relation, which are very nice relation, but the problem is that this relation, they are not correct. So if you do numerical simulation, what you find, for instance, in 3 dimensions is that you get around 1.5, not 1. And we know that for more than 4 dimensions is, the 4 dimension is not the upper critical dimension for localization. So you can do numerical simulation in 5 or 6 dimensions, and still you get a critical exponent which is bigger. So something is not working with this. Also, this is not strange at all. This is what I want to emphasize, that this is doesn't work. Because the problem is that it's always perturbative around the metallic regime. So you are taking into account only a very specific set of diagrams, which are these diffusons diagrams, even though you do that self-consistent. And the problem is that we know that this diagram, when we increase the dimensionality of the space, they will become less and less important. So actually, it's normal that this self-consistent condition does not give right result for the critical exponent. Also, in all these 2 approaches, it's not taking into account, as far as I know, the fact that the anomalous diffusion, right at the critical point, the diffusion is anomalous. And this is the prediction of the scaling theory. Okay, and then the proposal, what I did was to do the following, is that, so we know what is how the diffusion coefficient should go according to the scaling theory. So we know that. So this has to take into account somehow all the things that we don't know about the Anderson transition. So all the things which are not included in the self-consistent treatment. So what I did, I used the renormalization of the diffusion coefficient as is expected in the scaling theory, and I combined with the self-consistent condition. So essentially what I'm assuming is that, this is what is called semi-classical or quasi-classical, is that at the Anderson transition, you have a process of anomalous diffusion, and then you don't have any other correction. So it's like your ladder diagrams are given not for normal diffusion, but for the anomalous diffusion which is given by the scaling theory. So this was the idea. Then you can check. I mean, you only have to. I'm interested in this limit when the frequency goes to 0. I want to replace, this is the localization length, I want to replace it by this quantity, and I can repeat the same thing here. The only thing is that now I take into account the renormalization of the diffusion coefficient. And then I can repeat the calculation of for instance, for critical exponent. So it's simple, it's just to make an expansion of the integral, And then what I found is something which is slightly different. So what I find is that the critical exponent here is a 1 over d minus 2, which is the prediction of the self-consistent condition plus 1/2. And then what I'll show you that this is very close to what you get in numerical calculation. Okay. But let's now to look at a different other thing that you can look at in this very simple formalism. So you can compute level statistics. For instance, this guy is the 2-point level correlation function. So you can, if you do perturbation theory, and then you take into account only ladder diagrams. Okay, this is the standard result. So you can compute. This is the expression for this function, which is valid only when S is much larger than the mid-level spacing. I mean, S is much larger than 1 because this is expressed in terms of the units of the mid-level spacing. So the standard result that you do is that this is the expression, like the perturbative expression. But now, what I'm claiming is that this expression is also valid at the metal insulator transition if you replace the normal diffusion for this anomalous diffusion that you get from the scaling theory. And then you can compute properties. Of course, essentially, strictly speaking, you can compute properties only related. I could compute more complex objects, but with this is enough for what I want to do, because what I want to do is the following. I want to compute this quantity. This is called the number variance. This is for people doing numerics. It's something which is very easy to compute. So now, in the mid-90s, after computers became really powerful to do this calculation, this was something that people compute numerically at the Anderson transition. And then essentially, this is the fluctuation of the number of eigenvalues. So this tells you. So let's see that you fix a spectral window, and you count how many eigenvalues you have in this window. And so this function gives you the fluctuation of these numbers. So let's see, I fix this window. There are 5 eigenvalues, and then I move through the spectrum. Then it can be 6, 7, 8, 5, 4. So this gives you the fluctuation of the spectrum. And then with that, it's simple to do the calculation because we know this. So it's just a simple integral. And then what we get is that this is valid only for L is sufficiently big, is that it's linear. So this guy is linear. And this was precisely what people found in a numerical experiment, in numerical simulation. And now also, actually, you can compute this coefficient, okay? And then you get that. But this coefficient should be wrong, okay? You can compute analytically why it should be wrong. Because actually, in this calculation is included what is the critical dimensional conductance. But you don't know how to compute that. I mean, you don't know. You know. Actually, Shapiro, Abrams did it like a long time ago. I mean, this is one loop calculation. But this is one loop calculation. So it should be valid only close to 2 dimensions. Actually, what is strange is that this formula is consistent in both limits. When d goes to 2, this goes to 0, which is reasonable. Also, when d goes to infinity, this predicts that you get Poisson statistics. So this is equal to 1. And precisely this kind of limit, this has been recently got by Eisman and Warsaw in the case of the Cayley tree. So also it was found that the number variance has this coefficient, and this Cayley tree should be like the infinite dimensional limit of the Anderson model. Okay. So let's see that this is tentative. The value. This should be okay. The linear behavior. Just I want to mention 2 things. So the first thing I want to mention is that this linear number variance was also obtained by Schuler-Skolovsky in 88. Using kind of heuristic arguments, which are only valid in 3 dimensions. In principle, this kind of treatment is valid in any dimension. Also, I want to show that there is other expression for this, for the slope of the number variance by Cholker, Kraftsol, Lerner, I think in 96 or around this time, which it depends on the multifractal exponent, which is good for 3 dimensions. The problem with this formula is that if you go to high dimension, it doesn't work because it tends to 1/2. And we know that for high dimension should be close to 1. So I just want to mention. Yeah.
So the Eisenman-Morcel result, was that for the surface or the bulk of the Cayley tree?
In the Cayley tree, what is the difference?
Result for the canopy graphs?
Yeah.
Okay, so I've been chastised by Simonis for quoting this in a similar context because I think they treated the surface states rather than the bulk states.
But you know, in Kelly tree, it's almost its surface.
Well,
Okay. 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 So then we can compare with numerical results. So these are the this expression, and these are this formula, and these are the numerical results till 6 dimension that you can get, and it seems to be very good. So even I got surprised that it was that good. Of course, as I said, this exponent.
How did you get the L-bars in the numerical results?
What?
How did you get the L-bars in the numerical results?
I don't know exactly how you get the. I mean, I didn't do the numerics. Always, okay, I think now I understand your question. If you compute critical exponent, error bars should be understood, okay, with some. I'm saying that just because of experience. So you see many people saying something, and then you realize that this result was not right, because it's very difficult to get error bars when you do this numerical calculation, because it's one of the most difficult things to compute. And as I said, this value, this chi, is not it's not bad, but it's not really good.
sorry. So are these fits to one parameter scaling? Is this how these exponents are generally computed?
What exponent? This exponent?
Yeah.
No. This is what I explained. Is this
No, the ones with error bars. Sorry.
No. This is numerics.
Right. So in the numerics. How
Okay. Yeah.
So you assume one parameter scaling and then fit the
Yeah.
data. Okay.
Yeah. Okay, so this is what I want to say about this problem. And now I want also to talk about some problem which is somehow completely different, which are under what condition if you have a one-dimensional Anderson model with short-range hopping, because long-range we know what happens if we have long-range hopping. So under what condition you see a metal insulator under what condition you see metallic state. So I'm going to discuss that for quasi-periodic potential, non-quasi-periodic potentials. And actually, it's a work in progress. So this is actually was interested just to say that to a mathematical audience, just to see if it's something completely crazy or not, because it's something, actually, what I realized, it was something very mathematical. But let me first tell you my motivation, and then you will understand. So what you see here, this transparency, this is how I introduce my talks on localization, when I have an audience that didn't know about localization. So I said, your intuition about localization. Okay, so you place here a wave packet, and then here people, of course, you expect that it won't move much, right? Here, okay, you don't know. Here, intuitively, you may think that the particle will move, even quantum mechanically. But then Anderson said that this is not the case, or Towson said that this is not the case. And then somebody asked me, and this is one of the motivations to start this project. Okay, this is the random potential, but you know this is like handwritten, so it's not especially random, right? So what this person asked me, but how random must this random potential be in order to see this? What you said, in order to see localization, because obviously this kind of potential is correlated. Okay, it's not uncorrelated. This point, of course, is correlated with the other points. And at that time, I didn't know exactly how to answer this question. Even I don't know if it was a precise answer to this question. But somehow I forget. So then came the second motivation, where it was more physical or more practical. It was a conversation with Yora Sliaknikov, that he told me that they were working with coal atoms, and then they with this speckled potential, they have some very specific correlation. So in this case, you can create in this coal atom with optical lattice, you can create a random potential, but with some long-range correlation. So it's not delta. So they published this paper. This was essentially numerical and semi-analytical paper, and they found also localization. But the question is that what happens if you change that? If you make maybe this correlation long range even more? Okay, you decrease this value. Will you see a metal insulator transition? Okay, so this was the question. So this is why also I start working on this problem. Actually, it turns out that this model with this kind of correlation has been recently put in the study experimentally. This was maybe the first really experimental verification of Anderson localization. Here it was with spectral potential, and here was with multichromatic potential, which are a kind of quasi-periodic potential. It seems that in the years to come, we will see more papers now going to 2-dimension or 3-dimension, and they will be able apparently to compute things like critical exponent. But what do we know about localization, delocalization? So this is what I knew when I started the project. So what I knew was simply that, well, you know, the Bloch theorem, that if you have periodic potential, you should see metallic state, at least inside the band. For uncorrelated potential, you should see exponential localization for every energy and disorder. Then the next question to ask is, okay, if I want to see under what condition I can see metallic states, maybe it's easier to look at first for quasi-periodic potential. Okay? So for quasi-periodic potential, this is a standard Anderson model, and then you have this kind of potential. The standard case, which is called in the physics literature Harper model, in the mathematical literature almost Mathieu. It turns out that depending on the coupling constant, you get a metal, an insulator, or critical behavior, like a metal-insulator transition. This was proved by Hitomirskaya. Also, yes, I want to mention paper in the previous paper by Sinai, and in the physics literature paper by Harper, Aubrey, and many other people have papers about that. So don't feel insulted if it's not your name is not there. Also, so this was the result. This was no. Also, I found that there are even more recent results that if you can work with more general potential, like this type of potential, where this function is analytical because they have this exponential decay. And this was proved by Hitomirskaya and Burgain that you have also you can find a metallic state. It's a different condition. It's a little bit more difficult, but still you can find metallic states. It seems that it's conjecture that up to c to 3½ this is a function which are continuous and 1.5 times differentiable. You will see metallic states.
What's 1.5 differentiable?
I don't know. I mean, this was a conjecture that I saw. People told me.
Just the rate of decay.
Yeah. Yeah. And then you can ask the opposite question. So the opposite question is that what is the least smooth potential that can lead to a band of metallic state? So we see that up to this point we can see metallic state. And then this was conjecture. So the answer to this question is that a metallic band cannot exist if Bx is discontinuous. So if this function,
Metallic state, extended state.
yeah, absolute continuous spectrum. I call absolute continuous spectrum metallic state. Yeah. And so this was conjecture by Hitomirskaya and Aubrey and was recently proved by Damanik. So then we have, I was happy at that point because we have a window that nobody knew. It was a window between functions which are continuous and functions which belong to, who has some degree of differentiability. So we didn't know if we have localization or no localization. So then the next step was simple. So we start working with this type of potential. Okay? So Hitomirskaya Burgain work with exponential. Then we work with power law here. So in that case, you can control the differentiability of the potential. Okay? And then we found kind of physical way, simple way to see that why we expect to have metallic state for any alpha bigger than 0. So what we did is what people, something standard in the, especially in the mathematical literature, is to do what is called Aubrey duality, or just simply to go to Fourier space. So we put this equation in Fourier space, and then what we find is something interesting. So you see here we get this is the hopping term. So in Fourier space, the hopping term become long range. If we have this type of coefficients, okay. But this model, and then the diagonal term is this term, which of course is not random. But we know that for sufficiently large lambda, we know that we expect to see something similar to random behavior. And this type of model, they have been discussed by Levitov, Fyodorov, Mirlin in the physics literature. Of course, when this is random. Also in the mathematical literature, there are some word about that. So assuming that, then if we get localization, because for alpha, any alpha bigger than 0, this is expected to lead to localized state. Then we have delocalization in real space. So that suggests that any quasi-periodic potential, I wouldn't say any because you are a mathematician, maybe it's too strong. This type of potential, if they have some degree of differentiability, still we should see some kind of metallic state. So these are, for instance, numerical simulation for the dimensional conductance. This is for alpha equal to 1/2. Then we see that at the center of the band, we see metallic states. Then if we go far away, then we see insulator state. Because this is, this is a log scale. Well, it's not log because it's already log here. And then when alpha is equal, actually it's close to 0, then you see, we see insulator states, no matter how small is, we try different small disorders, or we always saw exponential localization. So far, so good.
No disorder is small, this A capital.
Well, a capital or lambda, okay, and then, at that time we were happy. So now we went to non-quasi-periodic potentials. And then first we did what it was in the physics literature, because remember, my motivation was try to write a nice paper about these cold atoms and then find some kind of metal insulator transition in one dimension with some specific type of correlation. And then we check in the physical literature. For instance, we found this prediction of visual croaking, which it can be described as follows. So they claim that you have a potential with some correlation. If you compute the Fourier transform, and then you find that it's 0 in some window of momentum. For instance, you can get that if you have a correlation which is like sine x over x. This is one example that you can get that. Then they claim that you should see a metal insulator transition. And the claim is that this is the Lyapunov exponent in the Born approximation is proportional to this the Fourier transform. So it should be 0. So if this is 0, you should see a metal insulator transition. But the problem, actually there are 3 problems with that. So the first problem is that even if the Lyapunov exponent is 0, this does not mean that you have metallic behavior. And also you can have higher order corrections, okay? And the higher the correction, actually people compute this higher order correction and found that for at least for many models in which you have this sk equal to 0, second order correction gives a Lyapunov exponent which is different from 0. But actually there is a third problem which is even worse. I'm going to say in my next transparency. And then also that there is this the paper by Lira and Moura, which they propose that if they have this kind of power law behavior, you should see metallic states in the spectrum. And the problem this is not generic. So it could be maybe for some potential, but you can imagine some potential in which this happen, and of course they cannot have metallic state. It's like if this potential increases with the space, you are going to get this behavior. But then if this increases with the space, the fluctuation increase. So then you cannot have localization. You cannot have metallic states. And then I just want to mention very briefly papers in the mathematical literature that you can see a metal insulator transition just by Kuhn, Simon, Sudriliad. If you have a sparse potential or decaying potential. Decaying potential means that in each point the disorder is getting smaller and smaller and smaller. And also there are many papers in the physics literature that they compute correlation, like by Lax, Schomerius, Effetov, Mirlin, other people. But in this paper, essentially the motivation is how they assume that you have an insulator, and then how things depend on the localization length. I mean, how this correlation affects the localization length. Then we went to we took the painful step to go to the mathematical literature. Initially it was painful because I knew nothing about that. But then I didn't find another way. I mean, the physicists, they didn't give any nice answer. So I went to Michael Eisman just for some help in Princeton, and then he gave me some papers, and then I started looking at this paper, and then I feel very, very ashamed that I didn't know anything about these papers, because they were really very nice results that even though I was working on this problem many years, I didn't know. From the papers by about the multi-scale analysis, the fractional momentum. So I reviewed almost all the literature. At the level, which my level was just to read the first page. The mathematicians typically are very nice because in the first page they give it like a summary of what they did, and then they just describe the details. But for me at that time was enough. Okay, and then what I found mainly for my problem of one dimension is that it was the Kohtani theory of ergodic operators, which it was quite a really powerful tool to say if you have condition under which you can have you cannot have what I see here absolute continuous spectrum. Now I become more mathematician. And then the main result, I believe, that is that if you have non-deterministic potential, you cannot have absolute continuous spectrum. So what is a deterministic potential? So a deterministic potential is a potential that if you know the values in some window, you know the values, you can predict the values of the potential. Of course, maybe for physicists, this is something, okay, and what, okay?
It's supposed to be correct in any dimension.
No, 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 this is only one dimension. Only one dimension. Well, here is the... also, the problem is that if the potential is deterministic, it doesn't tell you if you have absolute continuous spectrum or not. Okay, you have to use a different ways. Also, it's interesting that for this continuous potential, you shouldn't see you shouldn't see metallic states. But now, what is more interesting for maybe for physicists is that for Gaussian disorder, give you a
If I take a potential that is periodic and discontinuous, like a set of barriers that takes the problem, there is no absolutely continuous spectrum. I thought that you solve it with bands.
So what problem do you mean? So you have a periodic...
A periodic structure of barriers in one dimension.
Yeah.
That is solved in the first pages of the quantum mechanics.
Yeah.
Has to be ergodic.
Yeah.
It has to be ergodic.
Yeah,
Okay.
of course. I mean, this is ergodic theory.
Okay, so it's
Yeah.
really okay.
Yeah.
It is ergodic.
Okay. And then, but what is interesting is that if the potential is for Gaussian disorder, any decay. Okay, if you have any decay alpha bigger than 0, you won't see metallic states, and this is a rigorous result. So you have Gaussian disorder. Maybe Kotan is here, so maybe he can.
Get generality. What would you say? What do you think?
Yeah, maybe.
Shinichi, what do you think? That's true for arbitrary decay?
Yes,
Absolutely. AC spectrum.
Okay, so if you see that it's true, maybe we can continue. Then we can discuss later. Okay. Okay, and then because I'm actually it's quite late.
So this contradicts to what Israel had.
Yeah.
So basically it disproves that.
Yeah. Actually, for me, it was a disappointment because now my paper about colatoms was gone because it's I cannot. I have to come up to stop with something. I mean, because now it's not related to colatoms. Because in colatoms, you can always, at most, you can get maybe 1/x. You cannot really go to something, at least with a speckled potential. And now what I did was try to find potentials like with these properties, so they don't decay at infinity, and they have some type of differentiability. Even though I didn't know exactly what was the role, this was the main motivation. Just try to find this kind of potential. And actually, it's reasonable that this type of differentiability, because we know from physics that in one dimension, if the even close values for the potential they are uncorrelated, the particle will localize very rapidly because.
Does it mean this condition? Subtract the proper constant of the potential and then
No. This is no. What do you mean?
No, you have a correlation V of x, V of 0. You can choose some constant.
Okay, no, but you assume that you have a potential.
Center potential.
Yeah, you can do all this kind of trick. Also, I could say that in a different way, but this is not. Okay, so also we know that if we see metallic state, we should see ballistic motion. Okay, this is a prediction of the scaling theory. So what we did is just we try to smooth uncorrelated random potential. So we took uncorrelated random potential. Now we went to the literature, the opposite, like the literature of I don't know, engineers, or to see how you smooth a signal. Different ways to smooth a signal. And first, I just want to mention that all the numerical calculation was based in a finite size scaling analysis. That was pioneered in this paper by, of course, this is based on the ideas of Thouless and Skolovsky, Shapiro, 93. That this is how this works. So you compute some spectral correlator. In this case, the level spacing distribution, and then from that you compute some quantity like the variance of this number, and you use this as a scaling variable. And sometimes you can define some rescale variable, eta. And from that, you also can compute critical exponent. And then what you do is the following. So we know that if a diffusive metal, this variance should be some value. This is from random matrix. If the metal is clean, it should be 0. In the case of an insulator, it should be 1. And then what you do is just you compute, this is for the case of Anderson model, you compute this eta for different disorder, and then you look for a critical point, okay, in which is a scaling variant. So this is the metal insulator transition. And then on this side, as you increase the volume, it should go to the metallic. On this side, it should go to the insulator regime. So this is exactly what we do. So we start with one method, which is called Savitsky-Golay method. So, and let me explain what is that. So we take uncorrelated potential, and then we take MP values around this, around one given value and not. And then we replace this value of the uncorrelated potential by the best fit of these values to a polynomial of m degree. Okay? And then we repeat that for all values of the uncorrelated potential. So what we get is just this, for instance, this blue line here. Okay? And now let's try to check this idea. So as you see here, this potential actually is uncorrelated for long distance because only MP values are correlated. Okay, because if I compute this and then one point in this around this MP values, it should be uncorrelated if this is really far away. Also, of course, the resulting potential is not continuous. So we expect to see we don't expect to see a band of metallic states in that case, according to what I said. And this is exactly what we saw. Okay, so as we increase volume, the system always goes up. Okay. Tends to the insulator regime for any disorder and any energy. So that was like a check of the results. Then, well, the second thing we did was a Fourier filtering. So the Fourier filtering was very simple. So you take first the Fourier transform of uncorrelated noise, and now you remove a certain cutoff. Okay, so you remove any momentum after bigger than certain cutoff. Then you Fourier transform back to real space. So in principle, the resulting potential will be just a sum of sine and cosine function, will be analytical. So you can see it here. This is the red lines. Also, obviously, the correlations essentially will be constant. So we expect here a band of metallic state. Here could exist. It's not against any theorem or any.
This limit p of x for x going to infinity, does it exist? Is it a constant or it simply does not exist?
No. It should exist. It should be constant. If you have it's like a sum of cosine square, sine square j. It should be constant, I believe. And then what we did was a finite size scaling analysis. And then here we see, actually I wouldn't call that Anderson transition. I want to emphasize just that here, for sufficiently small energies, we see a metallic behavior. So physically, I mean, as you increase volume, you tend to the metallic limit, which is 0. So that means the following, is that if you have a particle here, even though this system looks like disorder somehow, it doesn't care about disorder at all. Okay, for this kind of potential. And now, just the final thing I want to say.
Can you explain what it means that there was this finite limit of the correlation function v of 0 and v of x? Yeah, there was already a question.
But
in direction. So does it mean that your potential just have some random some average? So what it means?
No. Your potential is maybe okay. Let me maybe in this case you understand better. So now we were working with a intermediate potential. So we were looking in the literature for integrable, I mean fractional integrable operators. Okay, so it's like this operator take a function, they integrated alpha minus 1 time. Okay, so in that case we took like a random uncorrelated potential. From we need to choose this region in order to have a nice continuum limit, and then we impose that the average should be equal to 0, and the fluctuation of the potential should be always the same for all, of course, all the.
Here they will be even growing.
Of course not.
No.
No, they won't grow. They won't grow.
Correlation, because it's like fractional Brownian mode.
No, but then okay, this is a good question. No, but then you are rescaling things. You think in terms of these guys. So it's not actually it's not increasing. I mean, it's increasing, but maybe very weakly, but it's constant. So it does not increase till infinity, because otherwise you would see localization. Yeah. No, this is. No, I understand what you mean, but this is something that we took care of. So it cannot increase. If the correlation increase, then you cannot get a metallic state. If the fluctuations are bigger and bigger and bigger.
Okay, we should discuss later because I feel that it's
Well, I
like something
understand.
like fractional Brown.
No, it is something like fractional Brownian motion.
But for fractional Brown motion, variance.
No, but then you rescale. Yeah, thing. I mean, I want to rescale thing in such a way
Later on.
that you have average and you have the same fluctuation. Because if you have this motion, then increase it. So you have to rescale thing in such a way that is bounded. Thing in terms of boundary condition. Okay, so we did the same. Okay, so now we have, with this kind of trick, we can also set the differentiability of the potential. So this, for instance, two examples for alpha equal to 0.2 and alpha equal to minus 0.2. Then you see that the difference between two is one is smoother than the other. So it's more or less the same global structure, but one is smoother than the other. And then what we found is that even though they have the same global structure,
The usual Brownian motion will be alpha equal 1 or is your
no, alpha equal to 0.
usual Brownian motion?
Yeah.
So
And then, this is also,
okay.
yeah. And then, of course, what we see here is that for alpha negative, we see a metal. So as we increase the volume, it goes to the metallic state. We decrease for alpha positive, then we see an insulator. Also, this is consistent with the calculation with the dimensional conductance. So from this result, what we can say in this model, it seems that the limit is in 1/2. Okay, is the limit of the less smooth potential that you can see metallic state. So essentially, the statement is that in that case, with the red line, if you have a particle above the potential, it won't feel interference effect. This
So
is
you rescale in the following way.
Yeah.
You first allow it like Brownian motion.
Yeah.
It increases,
Yeah.
say linear for usual Brownian.
Yeah.
It increases to
Yeah.
size of the system. In
Exactly.
And then you divide everything by
exactly. Exactly.
Oh, okay.
Also, you can understand that if you introduce a periodic boundary condition. So you can say, okay, if you have a Brownian motion, if hit one point, then it has to come back. It's another way to understand that. Yeah, but it's exactly that. And then by doing that, what you are essentially you are increasing the short range correlation of the potential. So this is why you make your potential smoother and smoother. Okay.
Correct that you cannot define what you do in an infinite sort of. In an infinite
No.
No. It won't
No.
have any reasonable
Okay.
limit.
Okay. So
Yeah.
It's not
It's in
sort
fact
of
not one
translation.
potential.
No.
Yeah, it's not transversal.
Yeah. That's that.
What I look at.
Yeah. Okay. Okay. So maybe now is my time. So I have something else to say, but it's better just to finish here. Okay. Thank you.
Okay, what are further questions? Yes.
If you look at time-dependent potentials, would be a closer approximation to that.
Sorry. So.
If you looked at time-dependent potentials.
But you mean time-dependent potential, but then under localization, do you expect to see under localization if you have time-dependent potential? Because then the disorder is not quenched. So if impurities are moving, in principle, you shouldn't see under localization. Or I don't know, it depends how you define the potential, but
Well, I mean, when you have quasi-periodic
Ah,
time, which would be, an approximation to an interacting system.
you mean that you have like quasi-periodic time dependence
That's right.
and the potential. I don't know, I mean, I didn't think about that. But in that case, maybe you can. In general, I would say that if you have some time perturbation, then I wouldn't expect to see under localization.
Yeah, that I agree.
Yeah. But in that case, I don't know. Yeah.
Returning back to this Israeli Krohin result, I remember there was some microwave experiment which very nicely done by Stockman group, which very nicely confirmed, in fact, the fact that they have probably the claim.
No. The claim, even in this paper, if you look at the paper carefully, they they are careful. No, the claim in this model, I'm saying that you don't see a you don't see metallic state. I'm not saying that they are exactly equal to a one-dimensional Anderson model. The point is that actually in this model you will see a huge localization length.
Okay, okay.
And then what they see is a crossover.
I see.
And they, even in this paper,
If they increase their definitely they will find.
The advantage of this model is that since you can since the localization length is much bigger, you can play with this with that.
Okay.
Actually, if you read the paper now, they also admit that then you don't see a transition because actually it was proved a few years later because people compute the second order correction.
No, I understand this. It's just huge localization lengths and play with it.
This
Okay.
would be lambda to the -4 instead of lambda to the -2.
Exactly, it's -4 instead of -2, so then it's something.
No, I understand.
Yeah.
Three short questions.
Sorry, can you raise your?
Three short questions. First, what is your definition of continuous or respectively discontinuous potential? Second is, how do you exactly reconstruct underlying dynamical system just out of two-point correlation function? And third, did you
No. Let's go step.
There's the deterministic potentials with exactly zero two-point correlation function.
Sorry, let's start with the last question. So you said that there are potentials.
There are potentials. Tom, can you tell more about that? There are deterministic potentials with exactly zero two-point correlation function.
What do you mean by two-point correlation function?
V of x, V of y. It's cosine of 2 to the n omega, fractional part.
So you said
transformation.
that
If over the dyadic transformation you take cosine, the
and this was I don't understand. Okay, that's fine. And what? So you have potential that you have correlation which is equal to 0.
My second question was, how do you reconstruct the underlying dynamical system to speak about continuity or discontinuity of the potential out of two-point correlation function of the potential, which does not feel the nature of underlying system?
I don't know if I understand your question.
Maybe you are restricted to Gaussian random potentials?
Okay.
Yeah, all these results are restricted. Okay. All these results are restricted to.
First question: what is your definition of continuous or discontinuous potential?
It's just what I show here. So let's see. Okay. So the definition is is here, for instance. So this type of potential is according to my definition is belong to C alpha. This kind of Bx potential
is that underlying phase space is necessarily a circle. But if you measure only two-point correlation function of the potential,
but when you say okay, but I don't understand.
Underlying
Sorry.
phase space.
First, well, this sort of discussion can be. Okay. Let's stop it here because it doesn't make sense. You simply don't understand each other.
On your first approach, the natural question that comes to mind: can you, with this length scale dependence of diffusion, can you also tell anything about the localization lengths, or have you thought about the localization lengths in a finite system? How does it depend on the size of the system?
What you mean is that if I compute the localization length in a finite system?
Yes.
Yeah, I mean, I did that in terms of energies. But I mean, what I compute is how the localization length depends when you get close and close to the critical point. But then you can repeat the same with the system size. So in that case, you have to repeat all things, but in terms of how the diffusion coefficient depend on the system size, and then you can get how things depend on. It doesn't really matter to work in energy, so in the system.
You get a single localization length, or it depends on the position in the system?
Of course, I mean, if you take a system which are close to the boundary, then it will be different. But if the localization length is, let's say, small enough, it should be the same, more or less. In what point you compute? I mean, these systems are homogeneous. So it should depend, but if you are close to the boundary, only if you are close to the boundary of the system, it should depend because it's not defined. You cannot.
How is the dependence?
I don't know. I mean, this is I don't know. What you mean is this kind of finite size effect? No, this is I don't know. I don't know. Yeah.
Basically, to the first part.
Yeah.
So basically, what you do, you just suggest interpolation formula for critical exponents from trying to.
No. It's not. Interpolation sounds that
Basically, you take a self-consistent
condition
and try to put in knowledge on this critical behavior.
No, the knowledge from scaling theory.
Yes,
Yes.
so this provides you with, I insist, this is interpolation formula, not more status of this, not more, which goes to large, from large to small dimension, basically.
Oh yeah, if you want to.
So
Yeah,
it's not, status, it's not more than that.
Or no less than that. I didn't know. I didn't know. Any way to understand analytically.
No, it's not okay. I even see from your result it nicely agrees with numerical data, but it's in this sense it's okay. I said what
It means that you don't insist that it's an exact statement.
No, of course. I mean, it's not a exact statement. This is something I'm glad to assume. That is not exact. Actually, it's a big jump because this is what I'm saying.
It's not exact. Then it's interpolation.
No, but interpolation means interpolation. No, interpolation means that I was thinking. I say, okay, here is 1/1/2, and this is 1/2. Why we just add them? Okay, this is for me. This interpolation.
You compare your.
No. I didn't. No. I didn't compare. I just did analytical calculation, and I compared this analytical calculation with the numerics.
I think this is some kind of improved self-consistency.
Exactly. I mean, exactly. This is it's not exact, of course. Yeah.
And reproduces a reasonable behavior.
Yes. Exactly. This was my intention. Yeah.
Okay. Further? More questions? We still have 1 minute.
Found any predict any properties of localization, these localization transitions that are in bad disagreement with your theory?
In bad disagreement, no. At most is our.
You just present one sort of critical exponent.
The other is like what you get if you do normal self-consistent condition. I mean, if you compute, for instance, critical
what I mean
disorder.
is that if you look at other critical properties.
Like for instance, you see like the critical disorder. I mentioned that if you compute critical disorder, I won't get any improvement from the result of these previous guys. It's not worse. It's just the same.
Okay, let's thank all our speakers for the.